Thank you very much. Let me thank the organizers for this opportunity to talk here. And let me start with my favorite example. My favorite example is this. Apparently, it has nothing to do with the Cahn-Hilliard equation, but many people in the audience will understand immediately that actually it has connection with this, with what I'm going to tell you. If you take a bowl and you put some olive oil and some vinegar, and you stir, okay, this mixture, then this mixture stays homogeneous for a while. Let's say that we are at room temperature, but then after a reasonable time, then the drops of vinegar tend to attract themselves, and you have islands of vinegar in a sea of oil, okay? And so this kind of phenomenon is called phase separation, and it's due to a competition. Let me say this in a very naive way. It's due to the competition between the entropy, which tends to mix the two components, and the attraction between molecules of the same type, vinegar, for instance. And this is a very important phenomenon. In the 50s, the last century, this was a phenomenon, for instance, observed when you are dealing with binary alloys, and you decrease the temperature of a binary alloy, and then you observe this kind of phase separation. But this phenomenon is much more ubiquitous in the sense that you can find it in very different situations. And this, if you are interested in checking how many situations are related to phase separation, you can, for instance, have a look at this. Is a bit of advertisement at the book written by Alain Miraville, who is here in the audience. I mean, you can find plenty of examples. But more recently, a very important field in which phase separation plays a very important role is biology. As Bressan was saying, biology is immensely complicated. Absolutely, I completely agree. But even more complicated than you may think. And let me start with biology. So let me start with, more precisely, with the role played, just 2 slides to make you understand what kind of role phase separation can play in biology. And then we will talk more about mathematics. And liquid-liquid phase separation in biology was proposed as a very important mechanism in forming structures called condensates in a membraneless cells. And it was proposed by Brangwyn and Hyman, who got the Breakthrough Prize in Life Sciences. And they also got many other prizes because of that. Because they discovered that phase separation plays a very important role in the membraneless cell, and the kind of formation of this phase separation is related to important diseases, for instance. Okay? So, I mean, I make the story very short because I have no time, but there is a huge literature about that. And so this is a cartoon which shows what I said at the beginning about oil and vinegar, essentially. Okay? But this happens also within the cell. And this, you see, for instance, this is a real picture. Human toe is a protein which plays a role in important diseases like ALS. Sorry, I told it in Italian, and Alzheimer. I mean, the way the phase separation takes place is important, is related to the efficiency of the neurons. I mean, it's immensely complicated. Okay, and so this is just to tell you that phase separation is very important. Okay, so now let's talk about mathematics. And in order to describe mathematically phase separation, a very common approach and efficient also not only from the theoretical point of view, because we can write down an equation, but also from the numerical point of view, is the diffuse interface approach. And the diffuse interface approach is based on these ingredients. Basically, you denote, you have a binary, a binary system, I mean, like oil and vinegar, for instance. You denote by phi the relative concentration difference, and then you introduce a free energy, and this free energy basically accounts for the competition between entropy and attraction between molecules of the same kind. And then you have also a regularization, this term here, which in a sense creates the diffuse interface. And the length here, I took one, but the length is the width of the diffuse interface is related to a parameter which I chose to be equal 1 here, not to, I mean, just to keep the things as simple as possible. And here you have, you see, you have this kind of, this is called a Flory-Hagen potential, and this is a non-convex potential. Non-convexity, of course, is a complication, as also Bressan pointed out before. I mean, non-convexity is a complication because you have many minimizers. And you will see how many minimizers you can have in this case, I mean, very many. And of course, you can also notice that this Flory-Hagen's potential has a part which is a continuous function because a phi goes from -1 to 1, but the point is the derivatives are singular at the endpoints. And this is a problem. This is a problem in order to interpret, as you will see, the notion of solution to the Cahn-Hilliard equation, which I'm going to introduce now. And by the way, just for your curiosity, this Flory got the Nobel Prize in chemistry. Okay, so he was an important guy in chemical physics. And this, the derivative, the functional derivative of this free energy is called a chemical potential. And it plays a very important role in describing the evolution of this kind of process through the Cahn-Hilliard equation. The Cahn-Hilliard equation can be deduced in this way. It was originally it was due to the functional to Cahn and Hilliard in 1958, and then the evolution equation was formulated by John Cahn in the beginning of the 60s. And you have a fixed law, okay? So the flux depends on a mobility, which is a coefficient depending on phi, times the gradient of the chemical potential. You use the mass conservation, and you end up with this kind of equation, which, if you read it in terms of phi, it's a fourth-order nonlinear equation, okay? Where the mobility can depend on phi, and this is essential also for mathematical results, because if you take a constant mobility, you can say certain things. If you take a degenerate mobility, so which is 0 at pure phases, 1 or -1, you have another situation. If you have a non-constant mobility, you have another situation. We will discuss about this because our talk strongly depends on the choice of the mobility. And so you have this equation, okay. So a brief story about this equation, but this story is referred to the case in which the potential is the logarithmic potential, the Flory-Hagen's potential. I just show it to you. In the sense that there is also a literature in which the logarithmic potential is approximated by a polynomial function, okay? But in that case, I mean, things are a bit simpler, okay? So the story starts with papers by the Bush and Kemochi in constant mobility, and then, I mean, you have a quite speaking essentially of well-posedness and regularity, you have quite a good picture, I mean, quite a complete picture, I would say. The case of non-degenerate mobility is a bit more complicated, and indeed the results are very few, in the sense that you have the existence of a global solution, the existence of local strong solution. You see, of course, the assumptions on the mobility are important because it's a coefficient depending on phi, so the regularity also depends on the regularity of the mobility. And this is due, this dates back to a paper by Barrett and Bloe, and that paper, if I'm not mistaken, contained a small mistake regarding the uniqueness. And this was fixed in a very recent paper by Conti, Galimberti, Gatti, and Giorgini, and where they proved the well-posedness of global strong solutions and instantaneous regularization. You expect that in a sense, but proving is another thing, as you know, but only in 2 dimensions. So basically, in 3 dimensions, you are the existence of a global weak solution, no more. Then you have another case, and this is particularly hard, and almost completely open, the case in which the mobility degenerates at pure phases. In the sense you have a mobility like positive constant times 1 minus phi squared, okay? And in this case, the only result I know, personally, is due to Hilliard and Garcke, and it dates back to 1996. And it's just the existence of a notion of weak solution, which is even weaker than the usual variational solution. I would like to focus on this issue. I mean, the behavior, the long-time behavior of a single solution. Okay? Because it's open in the case, as you will see in a minute, in the case of non-constant mobility. It's almost open, I would say. Why it's so difficult? It's difficult because if you look at the stationary problem, okay, which has this form, then here we are at least in 2 dimensions, okay, 2 or 3 dimensions. It can be shown that this kind of problem has a continuum of solutions. So you cannot expect that since you have a Lyapunov functional, then you easily deduce that you have a convergence to a single equilibrium, okay? Because you cannot do that. There are counterexamples. Okay? And so you need to use, in this kind of situation, you need to use a special tool, which is called the Logarithmic-Simon inequality, which can be used provided that the nonlinearities are real analytic. Okay? This is the major tool. Okay? And in the case of constant mobility, it was proved by Abels and Wilke that indeed you have a convergence to a unique stationary solution, okay, in the case of constant mobility only, 2 or 3 dimensions. Okay. This was the first result in this respect, basically, the first, big result with the logarithmic potential, or Reagnitz potential. In the case of non-degenerate, of course, in the case of degenerate mobilities, you don't have anything because you have just the existence of a solution, say. Existence, not even uniqueness, but you may expect that because you have degenerate mobility. So in that case, usually it's a very delicate matter. In the case of non-degenerate mobility, the only result is a recent result in that paper I just mentioned before, but they use a technique which is very similar to the one used by Abels and Wilke, but they are able to prove this only in 2 dimensions and for rather smooth mobilities, say C2, because they exploit the regularization of the solution. So the point is this, that when you have, what happens, to make it short, what happens if you have just a global solution satisfying an energy equality or even an energy inequality? Okay. This is typically the case, for instance, in which you have a Navier-Stokes system in 3D coupled with Cahn-Hilliard equation. This is a typical example. Here, in that case, you just know the existence of a global solution satisfying an energy inequality. Can you say something about in that case? Can you prove that any global solution, weak solution, does converge to a unique equilibrium? This is the issue. Okay. Okay, so let me describe briefly the result obtained by Abels and Wilke, what kind of techniques they use. They exploit the regularization of the solution. They can do it, of course, because they are dealing with constant mobility. And then they prove that the trajectories are precompact, and they prove that the distance of a given trajectory from the omega Lipschitz set goes to zero with respect to a certain norm here. Okay. Then they prove that any element of the omega limit set is a stationary solution, so it solves the stationary problem I described before. And then they prove that this omega limit set is compact in an order continuous space of functions because all the elements, all the stationary solutions are uniformly separated from the endpoints, namely for the pure phases, okay? So they are smooth functions, essentially, okay? They are separated, but in particular, the potential is real analytic when you compute it on the stationary solutions because they are away from pure states. And then, and this is crucial, they prove, taking advantage of this compact embedding, they prove that each solution for a sufficiently large time, since it's very close to the omega limit set, it is also separated. And this allows to prove, to use the Logarthe-Simon inequality because you are considering your free energy, and your free energy is a real analytic because you are working on a set, from a certain time on where the solution is separated from -1 to and 1. Okay, so it's real analytic. So you can use this inequality, which is crucial in order to implement, to finalize the argument and to show that actually your solution phi converges to a single equilibrium. Okay. And the value of the functional can be proved does not depend on the element of the omega limit set. I mean, this is epsilon E, script E infinity. And then they make use of the energy identity. And they conclude, by using this combined with the Logarthe inequality, they can prove that the gradient of mu is in L1. This is quite unexpected because, I mean, it's not an energy, standard energy estimate, okay? Indeed, you have to use the Logarthe-Simon inequality. But once you have that, then you go back to the equation and you prove that it's in L1 also the time derivative. And once you prove that the time derivative is in L1, you are done. Because you use the fundamental theorem of calculus and you prove the convergence to a single stationary state. Of course, in a higher norm because you can use relative compactness. So this is more or less the argument. So you exploit the separation property, this called separation property, I mean staying away, uniformly away from -1 and 1, only for large times. But you need regularity, okay, of solution. And so it's a very flexible approach, which has been extended also to other systems like Navier Stokes Cahn-Hilliard system, and also to multi-component system. I mean, multi-component Cahn-Hilliard equations, for instance. But the drawbacks are the fact that you need asymptotic regularization, you need an energy identity, and so it's difficult to import this technique if you want to analyze, for instance, the Cahn-Hilliard equation with non-degenerate mobility in 3 dimensions. Okay? Because it's true that in that case you have the energy identity, but you don't have the regularization. And what happens if you have, in addition, a coupling with the Navier-Stokes system? In that case, you don't even have an energy identity. Okay? So this is our idea. I mean, the idea is to use a new approach in which, under a very general assumption on the chemical on the density, the potential density, in the sense that, of course, logarithmic potentially it's okay, but you can even take a much more general thing. The only real requirement is the strict convexity and the fact that it goes to plus infinity and minus infinity at the endpoints, the derivative, first derivative. And then you take only continuous mobility, okay? And then you assume that you have a global weak solution satisfying an energy inequality, which is actually an inequality for the Cahn-Hilliard equation case, okay? But I state inequality just because I want to consider also the extension to Navier-Stokes, to a coupling with Navier-Stokes system. And the main result is this. You have a bounded domain of class C2. Maybe here you can, I don't know if you can just take a slightly more general domain, but in any case, you take a finite energy datum with a spatial average, which is, that assumption means simply that you start with an initial datum which is not a pure phase. Okay? And then for any global weak solution, okay, originating from this initial datum, which satisfy an energy inequality, you can prove the convergence to a unique equilibrium, only with these ingredients. Of course, you have to change a little bit the strategy, in the sense that you needed to introduce a weaker notion of omega limit, using only weak convergence. You have to proceed showing that it's non-empty, that any elements of the omega limit set is a solution to the stationary problem. Sorry for this typo. And then, first big step is to show that the trajectories are precompact in H1, because here you don't have regularization. So you have to prove it by hand. And exploiting the energy inequality. Then you prove the boundedness of the omega limit set. I mean, this is okay because once you have the omega limit set, this is a stationary problem. I mean, you can do it. I mean, this is not a big deal. But then, since you no longer have the injection in L infinity of H1, because you are, for instance, in 2 dimensions and 3 dimensions, then you have to use the separation property, but you cannot longer say, okay, my solution is close in a C alpha norm to an equilibrium, and so it is also separated for H times. Here you have to divide your set into 2 parts, a good part and a bad part. A good part in which you can actually prove the separation property. I mean, these are technical things which helps in order to control, I mean, to do this, to introduce 2 kinds of sets. This setting, the set for a sufficiently large time, this set where the gradient of the chemical potential is bounded by a constant, time t. Here you can prove the separation property on this set. Okay, using the George's iterations on an elliptic equation, this one. This is very technical, but it has been used also in other situations. Okay, but only on that set. On the other set, and so in that case, okay, on the set of good times, say the set in which you have the separation property, then you can use the Logarithmic sum inequality. This is okay because you are separated, the function is real analytic, it's fine. In the set of bad times, which are actually good times in a sense, I mean, you have a hyperdissipation because your gradient is greater than m, and so the ratio is greater than 1, and so you simply get this estimate. You can control this by this ratio here, because it's 1 less than or equal than the gradient of u over m. And so you end up with an inequality, putting together the set of bad times and set of good times, you have an inequality like that. And in this case, you can exploit a lemma by Feyerabend and Simondon, and you can prove the same result Abels and Wilke proved, namely and all the papers were related to this kind of approach, the fact that the gradient of mu is in L1. And so you deduce the convergence to a single equilibrium. Okay. And so this is, in a sense, a way which maybe allows us or others to extend this kind of result also to other problems, okay, in which you have just a few ingredients, okay, like the existence of a global solution and the validity of an energy inequality, which means dissipation. And a significant example is this. you have a model proposed by Abels, Garcke, and Grün it's a Cahn-Hilliard-Navier Stokes system. So here you have also fluid, okay, like in phase separation at the beginning, phase separation in fluids, okay? And so you have a Navier-Stokes equation which is modified because here the density is not constant, but the fluid is incompressible. And so they proposed a model which is, which has been studied by many people, both theoretically and numerically. And this big J is this mass flux essentially, okay, which depends on the difference of the densities of the two fluids times the mobility and the gradient of mu. So it's quite a complicated model. There are results, theoretical results, but we just need the existence of a global solution and the validity of the energy inequality in 3D. And this has been proved under these assumptions, essentially. But the mobility was a little bit more regular, but you can do it also for continuous mobility. And you assume the viscosity bounded from above and below. The density is a linear combination of the two densities. S is phi, actually. It's a function, it's substituted by phi in the model. And then you start from this kind of result, from initial data, essentially finite energy data, and with the condition that the initial datum for phi is not a pure phase, you have a global weak solution satisfying an energy inequality. This was due to Abels, Deppner, and Garcke. But what you can do is that you can split the original energy identity, can be split into two parts. One for the velocity, with this, of course, with these terms, this additional term, which comes from here, from the Korteweg force. This is a capillarity force. Okay. And then you have the same term here. Of course, if you add up the two inequalities, you get the original energy inequalities. But you can split up, and this is very essential, okay, in order to implement, to extend our argument. Once you do that, then you can do it. You can prove it. You can prove that any global weak solution originated from initial datum, suitable initial datum, this one, okay, we satisfy the above energy inequalities, which hold, if you have the original energy inequality, then you have the convergence to zero of the velocity field, which is a volume average velocity, because you have two components. And then you prove also the convergence to a unique stationary state, a unique stationary solution to the Cahn-Hilliard equation. So you extend the result. And the conclusions, we have found we think, a new method, which is more flexible to prove the convergence to a single equilibrium in cases in which it's not trivial, because you have many stationary states, and so you have to use special tools. And probably, we are thinking of extending this method also to other models and, for instance, multi-component systems on the case of different boundary conditions, like dynamic boundary conditions, and other models, but it's not taken for granted. You have to think about it. And, okay, thank you for your attention. Let me say that those ones are not Christmas decorations, even though they are like them, but they are the so-called GUV, giant unilamellar GUV vesicles. So they are lipid vesicles in which phase separation takes place, as you can see here. Okay, this is an essential bibliography. Thank you very much.